formal definition of a limit is one of the more difficult things that you'll look at this semester and try to understand. There's a lot of things happening here. We've got a limit as x approaches c of some function f of x that's going to be equal to L. We've got these really small values, epsilon and delta, greater than 0, so they're small positive values. We've got a couple of inequalities that involve absolute values. A lot of kind of difficult things to look at and understand here. So let's start just with a basic graph, and you can see this graph here on the right hand side. Essentially what we're saying is that the limit of the function f, so f is this line here that we have in this light blue here, that's our f of x. And as we approach c from either side of c, so as we approach c from both the left and from the right, we're saying that the value of this function will approach L. And as we can see, when we approach c from the left, it kind of approaches L from underneath. When we approach c from the right, it kind of approaches L from the top. That's not really important, but we can kind of see what's going on there. So what does this definition tell us? How does this definition help us with trying to understand what's going on here? Well, essentially, the way we need to read the definition is that someone else gets to pick epsilon, right? We're making the claim that this limit is true, that the value of this limit is equal to L. Someone else gets to pick epsilon, and then we have to find delta. So that's the first thing to understand. Someone else gets to pick epsilon, we have to find delta. No matter what epsilon they pick, no matter how small, we need to be able to find a delta. If we can't, then we can't claim that our limit exists. But if we can find a delta, then we can claim that our limit does exist. Now, we need to find this delta such that if 0 is less than the absolute value of x minus c is less than delta. All right, that's kind of the first weird piece. All we're really saying there is that we're going to create kind of a boundary around c. So there's going to be some value on the left, which is really c minus delta. And there's going to be some value on the right, which is c plus delta. In other words, the expression 0 is less than the absolute value of x minus c is less than delta is the same thing as saying that negative delta is less than x minus c is less than delta. And excuse me, I shouldn't have the absolute value signs there. It should be negative delta is less than x minus c is less than delta. And if we add c to everything, we get c minus delta is less than x is less than c plus delta. So our x is some value in between these parentheses. We have a parenthesis on the left, parenthesis on the right. It creates an open interval here. The 0 that you see just simply excludes c, right? The definition says that the function may not be defined at c. So the 0 just simply allows for that, so we don't have to worry about dealing with c. But anywhere to the left of c, up to c minus delta, anywhere to the right of c, up to c plus delta, that's where we get to choose our x values. That's where our x values come from, and that's really what this thing says. That's kind of reinterpreting that first statement. Now we need to find a delta such that whenever that's true, whenever we pick an x in between these two parentheses, that will end up with an f of x that is somewhere in between a comparable set of parentheses but that involve epsilon. So the absolute value of f of x minus epsilon part really kind of says that we have a boundary up here, which is L plus epsilon, and a boundary down here, which is L minus epsilon. We have to pick our x's such that this is true. So picking an x such that this first statement is true, 0 is less than the absolute value of x minus c is less than delta, means we have to pick an x in this range. And that x has to go to a y value that's in this L plus epsilon to L minus epsilon range. In other words, if we take a look at the absolute value of f of x minus L is less than epsilon, that's the same thing as saying negative epsilon is less than f of x minus L is less than positive epsilon, or adding L's everywhere, L minus epsilon is less than f of x is less than L plus epsilon. So someone else gets to pick epsilon. That is, how close do we have to get to L? That's really all epsilon tells us. We need to be able to find, that is, calculate a delta, such that as long as x is within delta, less than delta away from c, that when we plug that x into our function, we end up less than epsilon away from L. And if we can do that for any epsilon that anybody can ever pick, no matter how small, then we can say that our limit really does exist and that it is true.